Hello, my name is Craig Otto. This is Statistics for SPC, Operational Excellence, and today we're going to go through the second round of hypothesis testing. So with that, we'll go ahead and get started. Last time I kind of went through some of the basics and some general things that we need to know before we get into the hypothesis testing itself. And what this is going to be about is how does this hypothesis testing work. So I'm going to take you step by step here. When I started last lesson, I went through and I showed how you had a distribution and then you had what was called this critical region. And when that mean of the distribution fell into the critical region, that's how you know it's statistically different. So I'm going to walk through that and how that's done here. First of all, you have to have that initial hypothesis. And if you remember, it's a population mean is equal to another population mean. Okay? So you want to state that, and then you also want to state the alternative hypothesis, meaning are you doing a one-tailed test, a two-tailed test? Is it going to be a left tail or right tail? Whatever that alternative may be, you need to state that in your test. Okay. All right. Now, the next thing, which a lot of people sort of skip over, and you really can't do this, but you can't skip considering the assumptions. Number one, the data has to be normal for both distributions. If it's not, these tests are not going to be meaningful. The other thing is you need to know whether the variation is equivalent and whether it's not equivalent. It's a big deal. It determines which test you can and cannot use. Okay, so just be conscious of that. The next step is to select the appropriate test and distribution. As I mentioned, it makes a big difference if something's not normal or if it is. You've got to know that. And then the other thing is selecting the right test, knowing how many samples you have, whether the variation is equivalent or not, whether it's a proportion, whether it's means. All of that plays a role in determining which test. And as we go through this today, I'm going to kind of introduce you to all the different types of tests. But in the next lesson, I'll take you through how do you know which test to use and how does it work. Okay. So let's say in our example here, we've selected our normal distribution. Okay. And next thing we need to do is determine what significance level do we want. In other words, how much of our critical region are we looking at? Do we want 90% confidence where our alpha would be 0.1, that 10%? 10% would probably be out in here somewhere. Or do you want an alpha of 0.05, which is 95% confidence? That's where I have my critical region set. Okay. Or maybe you want something tighter, like a 99% confidence interval, where your alpha would be like 0.01. Okay. So that's step 5, is determining what do we want our significance level to be. Okay. Now, step 6 is where we compute the test statistic. And what we do is we take each distribution's data. What I mean by data, we'll take their mean, their variance, the number of samples they have, and create like a z-score, if you will. And then we'll do that for the other one. It creates a z-score for the second distribution. And then what it does is it compares the two. Okay? And that test statistic that comes out is kind of like that z-score. And you can see in our example here, we have our distribution, the first one in the blue, but the second distribution, the mean ends up being that test statistic. So if you can imagine a distribution in the background here with your mean between, well, it looks about like 1.75. That's like a z-score. So think of the past lessons. Just imagine that as a z-score. That's called a test statistic when you're talking about hypothesis testing. Okay? And then the next thing we need to do is compute the p-value. And the p-value is just basically finding the area under the curve from the test statistic point to the right. Okay? So from that 1.75 on up to infinity, that's going to be your p-value. Alright? And then we can decide whether to reject or not reject our hypothesis based on that p-value. So if p is less than alpha, that means that the p-value, that the test statistic would be somewhere in the critical region here. That means we would reject the hypothesis that these distributions are equivalent. Okay, does that make sense? If your p-value is less than this critical region, that means we reject it. That means that they're not equivalent. There's enough evidence to suggest that they're not equivalent. Okay. Now, if the p-value is greater than alpha, which it is in this case here in this example, my p-value is greater. My p-value is probably like, I'll say 0.15, and my alpha was 0.05. So what that means is that test statistic is not in that critical region, and there's not enough evidence to reject, so we fail to reject. Okay, so that's kind of how hypothesis testing works. The test statistic is the challenge. I think that's where people struggle to figure this out, because once you get the test statistic and that p-value, it's really pretty straightforward. You know, going forward and to calculate that test statistic, you'll find that, you know, Excel and the calculator get that for you, but the challenge is just knowing which test to use, and then from there it's pretty straightforward. You just compare p-value to what your significance level is. Okay, now as I stated, I'm going to show you all the different tests and sort of the math behind them. No need to get hung up on it, but just kind of know some general reasons as to why, you know, we have the different tests. For example, there's two different z-tests I have here, and keep in mind your calculator does all these different types of tests, so don't worry about doing the math on this. You know, that can look pretty scary, but don't get hung up on that. I just wanted to show it because so you know it does exist. And what this calculation is your test statistic in each of the different situations. Like on a z-test, usually your samples is greater than 30, and the biggest thing here is your standard deviation is known. Remember what I said about the assumptions. If you've got to pay attention to them. Is it a normal distribution? Do you know your variance or not? So in this case, on a z-test, biggest thing there is your variance is known. Okay, now there's something also called a t-test. So you can see a one sample t and a paired t. That's when you have a sigma unknown. Okay, when you're not sure about your variance. And you can see the difference between each of these tests. A one sample t-test, that's when your population is greater than 30, and when your population is less than 30, that's when you use this paired t. Okay, so that's just an example. Here we go on to some more t-tests, and again you have t-tests for equal variance and unequal. Okay, you can see that some of the criteria for each of these. Okay, and again that criteria is so important, so that when you read a problem, you just have to look back at this criteria and say, yep, that's going to be a two sample pooled t-test, or you know, that's going to be an unpooled. When you see this pooled, what that means is equal variance, and unpooled means unequal variance. Okay. Sometimes you deal with proportions. You know, a proportion of defective, or you know, going into a hospital setting, a proportion of you know, maybe unhappy customers or happy customers, whatever it may be. So this is just comparing proportions. And you see some of the criteria here, whether it's independent observations and all that. Remember, pooled means that you know the variance, and unpooled means that you do not. And then this last set of test statistics we'll get into later. These are some of the more advanced ones, like a chi-square test, testing for the goodness of fit. That's when you're trying to basically determine if populations are equivalent, variances are equivalent. Same with the F-test. You're not looking at means anymore. You're looking at the variances. You're comparing variance. Okay. This is some of the, in case you're not, I showed a lot of math there, and this is just some of the subscripts of what each of those meant, in case you're interested. Like I said, the calculator does all those number crunching for you, so you don't necessarily have to worry about that. But I did want to show, some people are math nuts, and they like to see what goes into all of that, so I want to be sure to show you. Okay, now I mentioned the challenge of hypothesis testing is knowing which test to use, and that's obviously it's kind of overwhelming. I'm sure you're kind of worried about, I just showed you about 12 different tests there. How do you know which one to use? Trust me, don't worry about that. We'll get into that the next session. We're going to do this one by one, but I want to make sure that we understand this step by step. So, we'll learn about selecting the test next time, but this time I want to go through and making sure that we understand this p-value, because this is so important. This determines whether we accept, we reject the hypothesis or we fail to reject the hypothesis. So, and that's all relying on this p-value. Okay, so I'm just going to give you some further explanation. Again, p-value is just the area under the curve for the test statistic. So when you plug and chug the numbers into the calculator and it spits out this number, it converts that number into a p-value, which is just the area under the curve. Okay, so let's talk about comparing that value to the critical values. Level of confidence, when we talk about whether it's acceptable or not acceptable, you have to look at the critical value. Okay, so given that we're using the standard normal curve, mean of 0, standard deviation of 1. If I say I want 95% confidence, now depending on what type of test you're using, that critical value can change. So if you're using a one-tailed test, in other words, your alternative would be that they're not equal, or excuse me, that it's a left-tailed test or right-tailed test where one is greater than or one is less than. That's the one-tailed test. So that would be an alpha of 0.05. Okay, and that 1.645, that's the z-score for 0.05. Okay, so that test statistic would be compared to this 1.645. Now, if you're talking about a two-tailed test where you're saying it's not equal, now because you have two tails, you have to divide that 0.05 by 2. You can see in these examples, that's what they did. That 0.025 test statistic got divided into 2 because it's a 0.05 total for 95% confidence. Same thing for the 90%. If it's for a one-tailed test, it's 0.1. The z-score value for that would be 1.28 equivalently. Two-tailed test, you just have to divide that by 2. So it would be 0.05 on each tail for the 1.645 z-score value. And then 99% confidence, you can see 0.01, but then if it's two-tailed, you have to divide that by 2, so 0.005. Okay, and you see the z-scores corresponding to those. Okay, so in these examples here, if your test statistic was minus 2.47, and you needed a 90. So that's where they drew this little test statistic in here, right here. That value for P, or area under the curve, is this 0.0136. So you can see the area under the curve is 0.0136. Now, that is less than that critical value of 0.025. That means we reject the hypothesis. Okay? Remember, if it's to the right of that or inside here, we fail to reject. If it's past these values, we reject. Okay? And like this example down here, our p-value is right here. Okay? And the area under the curve represents all of this. So because it's inside the critical region, it's okay. We fail to reject. Okay? But if that value would be to the right of the pink or to the left of this pink over here, we would reject. You can see here, rejection region. If it falls in here or here, we reject. Okay, so for p-value, only this is the most important thing you need to know. If it's in that critical region, you reject. If it's not, if it's between, you fail to reject. Okay, very important. As I've mentioned, you can do this hypothesis testing in Excel or on a calculator. And what I'm going to do is mainly on the calculator, and I would probably use that the most because the calculator is capable of doing more tests than Excel is. So I think we should probably stick with the calculator, and you'll see that in the next few lessons. We'll be doing a lot of work with our calculators. So make sure you got your batteries in there and ready to go. And we'll be going through and doing all these different types of hypothesis testing. Okay? Alright, we will see you next time.